go ahead and start by writing what I have at the top. Add this into your notes. Before we move into the types of IMFs, I want to make sure that we review the concept of IMFs and compare it to what we've been learning about all along, which are bonds. Remember, we said in the last lesson that IMFs are intermolecular forces. So these are interactions between molecules, between one molecule of H2O and another molecule of H2O. It's what holds and attracts molecules to one another. We compare that to bonds, which are intramolecular forces, the really, really strong forces that hold atoms of a molecule together. And it's important to remember and just make sure that we keep stressing this point. Intermolecular forces are infinitely weaker than bonds. And that the intermolecular forces are the mainly responsible for determining a compound, a covalent substance's melting point and boiling point. The stronger the IMFs, the higher the melting point and boiling point. You can see here I have it starred. The first of our IMFs are called London dispersion forces, or LDFs. And the LDFs are the weakest of all the IMFs by far. LDFs occur in anything that has electrons, so any covalent substance with electrons, which is all of them. So it's not as if LDFs only apply to nonpolar molecules, but they're only important for nonpolar molecules. And the reason is the other two types of IMFs are so much stronger than LDFs that once you have a polar substance, the LDF, even though it's there, it's negligible. The comparison I'd make, imagine that you had one job where you made $50 a week and one job where you made $1,000 a week. It's not as if $50 is nothing and you might not turn your nose up at it, but in the grand scheme of things, it has a lot less to do with your overall salary than the $1,000 job. If you take the $1,000 job away, all you have left is the 50. Now you have to account, there's nothing else to account for your salary, and you're also poor. But you get the picture. If LDFs are the only thing involved, and that means it's a nonpolar molecule, then you have to look at them. Once we move into polar molecules, we just put them in the rearview mirror and we concentrate on the other IMFs present. Real quick, just show you an animation. All right, quick link. If you take a look, you'll see this is a dipole-dipole interaction, which we'll come back to. LDFs, basically what it amounts to is when one molecule approaches another, since they both have electrons, and electrons are all negatively charged, you get what we call electron-electron repulsion. So think about this in terms of gases that are far apart from each other. As the molecules approach, the electrons from one, maybe the faster moving molecule, push the electrons from another molecule sort of to the other side. What it creates is what you see here. Right? When these molecules are around one another, you get temporary dipoles. They kind of move back and forth. These are really weak. They are super temporary, and that's why nonpolar substances are usually gases at STP, because they have such weak interactions. They're so temporary and so weak that they can just move away from one another freely, and that makes them gases. That's a property of gases. The next up is dipole-dipole, and this is occurs because of an unequal or asymmetrical uh, sharing of electrons. So this is all polar molecules. All polar molecules at least exhibit some form of dipole-dipole interaction. We said two poles. We break this up into its parts. Di meaning two, pole meaning end. Basically, in this case, positive and negative. The dipole-dipole, the attraction is temporary, but the dipole is permanent. permanent. Okay, so the dipole are permanent, but the interaction is temporary. So if you've got a molecule like HCl, that has what we call a permanent dipole. And we said this is because of the difference in electronegativity between those two atoms. So it's a permanent dipole. It's always there. The hydrogen is always partially positive. The chlorine is always partially negative. The interaction between two molecules of hydrogen chloride, it's brief. It's fleeting. That's the part that's temporary. A dipole moment, they talk very little about this in the Regents exam, but it wouldn't surprise me if it came back, is just a measure of the strength. All right, that term moment is referring to how strong the dipole is. And again, what determines the strength of this? It's the greater the difference in electronegativity, the greater the polarity and dipole moment. So you compare these two numbers, 2.1 and 3.2. Right? The difference there is in an overall 1.2 difference. If I look at another molecule that has a difference that's greater than 1.2, an electronegativity difference greater than 1.2, we would say it has a stronger dipole moment. And that means stronger the dipole moment, this is huge. Higher the melting point and boiling point. Okay, the more interaction you have between, or the stronger the interaction between the molecules, the harder it is to move them around, which would be melting, and to move them apart, which would be boiling. Look back at another animation, a little shock wave. Here's your permanent dipole, and we watch them interact. The interaction is going to be temporary, even though the dipoles are permanent. All right. So they would temporarily line up so that the positive end of one molecule interacts with the negative end of the other. The last of the IMFs are called hydrogen bonds, and I hate the fact that they call them hydrogen bonds, but the problem is they do. And it's important, I mean, I can't stress this enough. This is not, not a bond. Hydrogen bonds are interactions, but hydrogen interactions is too hard to say, so apparently they thought hydrogen bonds wasn't going to confuse anybody. This is actually a specific kind of dipole interaction. We'll say it's like dipole on steroids. It's because of the fact that hydrogen and any of the three most electronegative elements will form a really polar bond, that hydrogen bonds are the strongest of all the IMFs, by far. And the key is, if you look at a covalent molecule and it contains hydrogen first, it has to have hydrogen and fluorine, oxygen, or nitrogen. So hydrogen bonding is a special kind of dipole-dipole interaction, and it's the strongest kind. It only occurs in molecules that contain both hydrogen and one of the three most electronegative elements, fluorine, oxygen, or nitrogen. We'll take a look at a quick animation here. And again, this one we saw earlier in a previous lesson. It's worth looking at again. There's such a strong dipole moment in these bonds between hydrogen and oxygen that when the molecules interact with one another, uh, they kind of stick together pretty tightly. And it's why water at STP is actually a solid. It's at its melting point, and it takes to get to 100 degrees for water to boil when things like oxygen boil at negative 190 something degrees. Because oxygen itself, O2, is nonpolar. The hydrogen bonding in water makes it very, very polar, and that means these guys with hydrogen bonding have the highest melting point and boiling point. So when you're trying to rank substances in terms of their melting point and boiling point, anything with hydrogen bonding would be at the top of the list, have the highest melting point and boiling point. Anything with dipole-dipole would be next in line. Okay, that's a polar bond that doesn't include both hydrogen and either fluorine, oxygen, or nitrogen. And something with London dispersion forces is most likely a gas at STP. Okay, that's standard temperature and pressure. Okay, so gases at STP, dipole-dipole, might be gases or liquid at STP. And then things with hydrogen bonds tend to be liquids at STP, or even solids in some cases.